Hey everybody. So this is going to be just a quick video, hopefully quick video on kind of like defining functions, talking about the key behaviors of a function, what makes a mapping or a relation or a correspondence into a function, because it's specific. Just because there's a mapping or a relation or a formula doesn't necessarily mean it's a function. A function is very specific. It's defined very specifically. So we're going to just kind of do a quick overview, sort of for this is aimed for like the college algebra student. So just everything that you might see in a college algebra class. So what is a function? Well, a function is a relation or a mapping that produces for every input exactly one output. So a relation or mapping that produces exactly one output for every input. And that seems really simple. It is very simple. Something that's kind of tricky though is that this is actually saying two different things. There are two requirements here. The first requirement, one, every input produces an output. The second thing it's saying is that no input produces more than one output. So that's why we say exactly one. No more than one, no less than one. If there's an input that you can give to a function, it will produce an output, and it will produce only one output, assuming it's a function. So let's look at some examples, because that might make it a little bit easier. One function, we'll start with something that's like not necessarily a number, like a function in terms of like, you know, how we think of them in college algebra, because technically they don't have to be involving numbers. I guess this one is kind of involving numbers, but one relation or correspondence or mapping that is a function is mapping a person to their height. So here's, we'll start with me. I'm like, I don't know, I'm 5'10" on a good day. And then there's person A, and they are tall. They're 6'3". And then there's person B, and they're not quite so tall. They're 5'4". And then there's person C. And right, so like, I mean, it would just keep going on and on and on, just the person and then their height. But notice, every single person that I put over here, they're assigned a height. Like, what if I said, all right, well, there's person C, and they don't actually have a height, and so we'll just forget about them, and we'll move on to person D, and they're 5'7". You'd be like, what on earth do you mean person C doesn't have a height? It doesn't even make sense. So one, that would be really strange. Maybe equally as strange, what if I said something like this? What if I said, no, okay, person C, yes, they do have a height, obviously, and their height is 5'2", but also 6 foot. Right? That would be just as strange. You'd be like, what do you mean this person has two different heights that are a difference of 8 inches? Look, okay, yeah, maybe height kind of fluctuates. Today I'm 5'10", tomorrow I'll be 5'9.5" because I have bad posture. I don't know. That's kind of not what we're talking about here. This would be a really strange situation, right? If somebody had two different heights, it would be just as strange as if they didn't have a height at all. That's what we mean. Every input produces an output. No input produces more than one output. That is to say, in a word, every input produces exactly one output. Okay, let's see. Other examples might be birthdays. That's another good one. Everybody's got a birthday. How strange would it be if I started making this list that was on the left-hand side, names, and then on the right-hand side, birthdays, and I got down to person C and I said, yeah, they don't have a birthday. What? That doesn't make any sense. It also doesn't make any sense if I said person C had 2 birthdays. What on earth? That doesn't make any sense. So birthday, that's also a function. So these are the two things. If you're asked, like, is this a function? You need to check two things. Does every single input produce an output? 1. 2, are there any inputs that somehow produce 2 outputs? So let's see here. Some other ways that this might be represented. Right, so the table makes it somewhat easy to determine if it's if it's a function. Sometimes you might be given something like this, a correspondence as like a set of coordinates. So something like this. We'll say, here's our function. This is what our function hits. All of these coordinates and 5, 2. So these are like our coordinate pairs. 1, 2, 2, 2, 3, 2, 4, 2, 5, 2. Let's check. Does this, assuming that this is all of the inputs, does this fit the definition of a function? Well, does every input have an output? Yeah, assuming that the only inputs are 1, 2, 3, 4, 5, then yes, every input is producing an output. Does any input produce more than one output? No. The inputs only show up once, right? Even though each output is the same, that's fine. This is a constant function. That's fine. If every single input maps to the exact same output, that's still a function, as long as every input maps to an output, no input maps to more than one output. If, on the other hand, though, I said there was another point that corresponded here, which was 1, 3, like that, and I said this is also part of the mapping, then now this is no longer a function. Because even though every input is producing an output, there's one input that is producing two different outputs, namely the input of 1. It produces two different outputs, which would make this not a function. Okay? Let's see some other ways of looking at this, and I'm leaving some. Let's see, I'm leaving some things undefined. Maybe I should define those things now. And those things that I've left undefined, which maybe you've thought this to yourself, is what does it mean for something to be an input? What does it mean for something to be an output? So, and the terms that we use for those are domain and range. So the domain is the set of all, informally I want to say something like it's the set of all inputs, but it's kind of better to say, maybe it feels a little bit more precise to say the set of all intelligible inputs. So all of the inputs that actually make some sort of sense to put in, and in particular inputs that aren't going to cause problems. Then, so that's the domain. We have a term for the set of all outputs as well. We call that the range. And that one we can just say this is the set of all outputs of the function. Okay? So, let's see here. Here, let's find some good examples, if I have any. Well, let's just look at some graphs. So one graph that I think is helpful here is maybe the graph of, well, let's start somewhat simple. So we'll look at the graph of x squared. So x squared looks something like this. Something like that. So what are the set of all intelligible inputs for x squared? Well, what you might want to kind of think about is, are there any numbers that if I plug them into x squared, it causes problems? And the answer is no. There are no numbers that are going to cause problems. Give me any number, I can square it. It's going to come out to another number. It's fine. So the domain for this is all real numbers, which depending on how it's written in your class, might be written in interval notation. That's most common. If it's in maybe a little bit more math rigorous of a class, we might write it this way as the set of real numbers. These are the same things. What about the range? So the range is the set of all outputs. So domain, and as far as a function goes, domain, you're kind of thinking about what can I plug in for x? What is legal for me to plug in for x? Range is kind of like, what are all of, given all of the domain, what are all of the y values that are hit by our function? So if we look at the graph of x squared, here's the graph. It's all above the x-axis, except for right here at 0. It touches the x-axis there. Otherwise, it's everywhere above the x-axis. nowhere below the x-axis is this function present at all, which means that all of this area down here is not part of the range. Nothing is mapping to these. That's kind of what the range is. It's like the set of everything that is being mapped to. There are no values that map down here, but every value up here is being mapped to. So the range is 0 to infinity. Let's see. Another example might be the inverse, or I shouldn't say the inverse. Well, I guess kind of informally we call this the inverse of x squared, but it's really the square root of x, which it seems like those should be inverses. Without getting too much into the details, this is not necessarily the inverse. In fact, x squared doesn't actually have an inverse. But if we look at this, so here's the graph of the square root of x. It sort of does this. It's kind of like if you imagine taking this parabola and turning it on its side, but then only taking like the top half of the parabola. This is the square root of x. All right, so let's think about the domain for the square root of x. Well, the square root of x, again, when it comes to domain, you kind of want to think about like what are all of the values, the x values, that I can plug in that won't cause any problems. Another way of thinking about that, an equivalent way of thinking about that, is turning it on its head. What are all of the x values that I could plug into here that will cause problems? So think about it for a second. Like maybe pause the video, just take 10 or 15 seconds and think about, are there any x values that I can plug into the square root of x that might cause me some issues? And the answer is all of the negative numbers, right? Because, I mean, we do have materials, we do have tools to work with negative numbers. So like the square root of -2, for instance, we would say, well, that's an imaginary number. We would write that as root 2i, or I root 2, kind of depending on your preference. But the key point is that we can't map imaginary numbers on the real plane. There is a way of mapping them. There is something called the complex plane, and yeah, you can map imaginary numbers on that. But on the real plane, where it's a real line crossed with a real line, there's no place to map square root of -2. So in other words, the problem values for the square root of x are all of the negatives. Which means that the domain is everything except for the negatives. So 0 to infinity is the domain. Yeah, we can plug 0 into the square root of x. What's the square root of 0? It's 0. So yeah, we can plug that in, and we can map all of that. So kind of looking at the graph, you can think of it as like, if we look at this graph, what are all of the x values that the graph is sort of like being touched by? It's everywhere over here from 0 to infinity. How about the range? What is the range of this function? Again, it's the set of all outputs. The square root function, it strictly produces positive outputs. It doesn't give plus or minus. The square root of 4 is not plus or minus 2. The square root of 4 is just positive 2. So all of the possible outputs are all of the positive numbers. So also the range is 0 to infinity. And again, you can think of it like, what are all of the y values that are being hit by this function? And this function doesn't plateau, by the way. It sort of might look like it's going to like plateau and get flat. It's not. It's going to go off to infinity. So that's the domain and range of that. Let's look at one more function. One more function, just to kind of get an idea of domain and range, at least as far as the graph goes. Then we'll look at an equation and try to tease out the domain and range of the function. So here's one last one. We often call this the reciprocal function, 1 over x. And it looks like this. It's kind of broken into two pieces. And I'll draw it as best as I can, but it's got asymptotes, which means it gets infinitely close to certain lines, but it never actually touches them. So yeah, my drawing is not totally doing it justice. But here's kind of in general what the reciprocal function 1 over x looks like. So same thing here. What's the domain? What's the range? Well, on the one hand, we can sort of look at the domain on the graph. It's all of the x values that correspond to some kind of output. So yeah, everything over here is corresponding to some kind of output, some kind of output, some kind of output, and then this goes all the way off. And then here at x equals 0, there is no output. And then once we get just past to the positive side of the x-axis, again, there are outputs again. So I'll sort of write this. Actually, before I write out the interval notation for the domain, just kind of think about, again, looking at this like the function is 1 over x, you want to think about what are the problem values that I could possibly plug into this. And there's only one problem value for this. Can you see it? If not, again, take a second, pause the video, think about it. What might be a problem value that we could plug in for x that will cause huge problems with 1 over x? The answer is 0. If you plug in x equals 0, you get 1 over 0, and 1 over 0 is undefined. Just remember that. 1 over 0 is undefined. And just so you know, though, just kind of like a side comment, 0 over 1, that is defined. That's 0. So 0 over 1, 0 in the numerator, that's fine. 0 in the denominator, big problem. So you need to avoid a 0 in the denominator. So in other words, the domain here is everything except for x equals 0. How do we write that in interval notation? Well, we'll take every single positive negative number, every single possible negative number all the way up to 0, but we don't include 0. 0 is a problem. And then we will union that with 0 to infinity, all of the positive numbers. That's the domain. Range is actually the exact same thing. So again, kind of looking at this graph, what are all of the y values that are being hit? All of these y values are being hit by this sort of left arm of the function. All of those are being hit, but then when you get here, y equals 0, nothing is hitting that again. The second that, or the moment that you get above y equals 0, all of a sudden those values are being hit again by this sort of right branch. So it's the same thing. The range is everything except for 0. Negative infinity to 0, union 0 to infinity. If you need to convince yourself of that, one way that you could check that is, well, if I think that 0 might be hit by this function, I can try to solve it. What x value results in 1 over x equals 0? Well, this is equivalent to saying that x times 0 equals 1, which is not possible. In our number system, anything times 0 is always just 0. It's never 1. So yeah, there are no values, there are no x values that will produce 1 over x equals 0. So the range is negative infinity to 0, union 0 to infinity. Okay, so that's domain and range. Let's see here. One quick example. So suppose that we're given an equation, something like 1 over the square root of x plus 5, something like this, and we're asked to find the domain of this. So the domain, what you want to kind of think about is what values cause problems. Well, what problems can occur with something like 1 over the square root of x plus 5. So we've got a fraction, which means we need to be worried about having a 0 in the denominator. And we also have this radical right here. So we need to worry about anything negative being plugged into the radical. So in other words, we need x plus 5. Well, on the one hand, we need it to be positive, because it's under the radical. If x plus 5 turns out to be something negative, then all of a sudden you have a negative under the radical. So we need x plus 5 to be greater than 0, greater than or equal to 0, actually, just just to like not worry about the radical, but we also need to worry about x plus 5 being equal to 0, because if x plus 5 equals 0, then you have in the denominator the square root of 0, which is 0, and you'd end up with 1 over 0. So we need x plus 5 to be strictly greater than 0. That will give us all of the possible values that won't cause any problems. If x plus 5 is less than or equal to 0, you'll get problems. You'll either get a 0 in the denominator or you'll get a negative under the radical. So we want x plus 5 to be greater than 0. Well, solve the inequality. That means we need x to be greater than negative 5. So what is the domain of this? It's x greater than negative 5, or in interval notation, negative 5 to infinity is the domain there. Okay? And then the very last thing that I want to talk about is one-to-one. So one-to-one is like kind of a description of about the graph. So one-to-one, the sort of strict math definition is that so a function f is, and I'll write it this way, it's one-to-one if f of a equals b, f of b, and this is an if and only if statement, f of a equals f of b means that a equals b. So if f of a equals f of b, then a is equal to b, and then obviously if a is equal to b, then f of a is going to equal f of b. So yeah, I guess maybe that should just be one direction, because if a equals b and f of a doesn't equal f of b, then it wouldn't be a function. So maybe another way of thinking about this is that every output is mapped to by only one input. And the most informal way to think about one-to-oneness is that it passes the so-called horizontal line test. Okay. So let's just look at some graphs for some examples of functions that are one-to-one and functions that are not. So consider first just any linear graph like this. So, well, if we're given a graph, the easy way to test if it's one-to-one is the horizontal line test. Any horizontal line that I put through here is going to touch, assuming that it's in the range, is going to touch our graph only one time, exactly one time. So yes, whatever function this is, it's one-to-one. How about something like x squared? Oh boy, there we go. That's a little bit better. Is that one-to-one? No, it's not. So we can put a horizontal line right through here, and there's the horizontal line where it touches the graph twice. So no, this isn't one-to-one. And by the way, it doesn't matter that we can put a horizontal line down here and it doesn't touch the graph at all. That says nothing at all. That's just outside of the range. So your horizontal line needs to go through the range of the function in order to determine whether or not it's one-to-one. And you can sort of algebraically prove that something is one-to-one. Maybe I'll just do a quick example of that in the last couple minutes here. Suppose that we are given something like, I can do it down in this corner rather than using up a whole new paper. So suppose we're given something like f of x equals 3x plus 2. And we're just given that, and we don't know what the graph is. You should, by the way, if you're in college algebra at this point and you're learning about all this, you should know what this graph looks like, or you should be able to graph it. But suppose you don't, and you want to determine, is this thing one-to-one without looking at the graph, or maybe your teacher is asking you to algebraically prove that this is one-to-one. Well, here's what you do: is you, at the outset, you assume you have some f of a equal to f of b. How do we prove that this is one-to-one? Is that we need to prove that a equals b, that they're the same thing. So f of a equals f of b. Well, what is f of a? F of a is if we plug a in for x. So this is saying that 3a plus 2 is equal to f of b. What's f of b? It's if we plug b in for x. 3a plus 2 is equal to 3b plus 2. And then let's just simplify this equation down. And it simplifies down very quickly. So on the one hand, we can subtract 2 from both sides. If we subtract 2 from both sides, we get 3a equals 3b. And then finally, we can divide through by 3. And what do we end up with? A equals b. So yes, it's one-to-one. We've proved it. How would you prove that something is not one-to-one? Well, you can do something like this. So if we wanted to say, without the graph of x squared, if we wanted to show that x squared is not one-to-one, we might say something like, consider f of 1 and, like, assuming that this is f of x, f of 1 and f of negative 1. I might say something like, all right, well, f of 1 is equal to 1 squared, which is, sorry, why is it so difficult to, probably because of the contrast with the black, sorry. F of 1. What is f of 1? Well, f of 1 is 1 squared, so that's 1. What is f of negative 1? Well, negative 1 squared is also 1. So we have a situation where f of 1 equals f of negative 1, but 1 is not equal to negative 1. If this was a one-to-one function, then having f of 1 equal to f of negative 1, it should be the case that the inputs should be the same. So a equals b, but over here we have a counterexample. Two numbers, 1 and negative 1, that are not the same, but they map to the same output under f. Okay, so that is one-to-oneness, and I think that's where I'll stop this video. If you have any questions at all, let me know. I'll be happy to answer them.